Nice. So easy. Good stuff. All right. So, one thing that I wanted to mention for AC systems, I'm hoping that I kind of blew your mind once when we first drew up this chart that showed the relationship between voltage and current, right? Where my current is in blue here and my voltage is in red, okay? So ideally, again, he did a cool trick where he did what I was trying to explain, where at every point on here where we multiply the current by that point on the voltage graph, right? And our maximum power comes from the maximum on our amperage and the maximum on our voltage. So at this instant, we are transmitting the maximum power to whatever we're powering, okay? Now, something can happen in AC systems that actually causes this current trace and this voltage trace to become decoupled. It's called a phase displacement, where even though we would expect the current to be highest when our amperage is highest, that is only true for a perfectly resistive system. If there is capacitive components, if it has some amount of capacitance, which everything in the real world does, or some amount of inductance, which again, everything in the real world does, okay, these two curves actually won't line up exactly. There will be a little bit of a delay. Oh, that was bad. Hold on. Okay, where this will go up, but then the cycle won't go up until a little bit later. Okay, so it'll be more or less the same. Sorry, it should not be so high. Right, it'll be the same as what it was before, but it'll be shifted. There we go. That's kind of what I wanted to go for. I wish I had different colored markers. I'll just do a dotted line on this one. Okay, so the dotted line is our current. Okay, so you see how it is a little bit out of phase. It's this far off. If we scooched this dotted line this far over, it would be perfect. Be lined up, right? This difference, okay, is our phase displacement. We call this two signals being out of phase, right? So if we have one signal that's going in this direction and one signal that's a little bit later, okay, they are out of phase by this much. When we have one signal that goes this way, okay, and then another signal that goes this way, they are out of phase, but they are out of phase by a whole signal or a whole half, right? That causes them to be inverses of each other. If we pushed this one over this far, this dotted line, it would line up again, right? That's being out of phase, okay? This difference, this offset too, so it lowers our peak available current, okay? So see how our maximum possible power is no longer what it could be because the maximum current no longer happens with our maximum voltage. So our max, P max equals V max times I, right? It's not at its maximum point, so it'll be lower. Okay, this is what we call power factor. The power factor comes into play, again, more in transmission. We're moving power from our power station or our generator to the thing that we're powering, but it nonetheless is really important to our system. We can actually add things to our system at the plant or at the generator to correct this power factor, literally called power factor correction. Okay, that literally shifts this waveform back over. It corrects the phase so the maximum aligns with the maximum and we get our maximum power back. So that is power factor and power factor creation. But I just wanted to introduce the concept, okay, that in a not perfectly resistive system, it is possible for the voltage and the current to be out of phase with each other, okay? That you would expect that more voltage would get more current, but in real life, that reaction can be delayed for reasons that we'll explain later. Okay, I'm gonna fly through a few things here, but please review them. Okay, again, these presentations will be online. This is all from the book. Okay, one thing I wanted to talk about was three-phase generators and three-phase generation. Why does it exist in the first place? One reason why it exists is because it gives really clean power. It gives really clean output, okay? Remember before, talking about the average power or the average voltage that comes out of a system, okay, when we have input peaks that look like this, okay, once we filter that, okay, the resulting average that we get looks like this dotted line. Okay, so it'll go kind of match the curve, and it'll go up and down and up and down. Okay, so the actual voltage V out that we get will vary by this much, you know, depending on when we check in on it in the cycle. It could be 110 volts or 105 volts, okay, and it's drifting all the time. But if we didn't do this, if instead we did more spikes, just like this, okay, or even better, we did relatively few spikes, okay, say we only did a few spikes like this, okay, but then we have another source of spikes that we interleave in that keeps the average nice and high. Okay, so the ripple is much less now. The voltage never is really allowed to drop very low. Okay, our new variance is very, very small. Okay, this is us adding our three phases. Remember phase displacement being out of phase? They're all the same voltage. Okay, they're all 120 volts maximum, minimum, RMS, right, as we just described. But they're slightly out of phase with each other. See how this one goes up as it starts? This one goes down, and this one goes up, but it's at a slightly different spot in the curve, right? It's a little bit earlier in the playback, so to speak. But when we put them all together, that means that, that the average voltage, right, at any given time that is adding onto the line will kind of ride this upper part. Okay, it's not really allowed to droop very much because one of the lines will come in and start to energize it. Okay. So, the three-phase power, the fundamentals of three-phase power is really just that we have three wires coming into the house, coming into the building. Okay, literally three conductors from the electrical supply. You have your A conductor, your B conductor, and your C conductor. Again, all of these conductors have 120 volts RMS on them. Okay, none of them are higher voltage than the other ones necessarily. They're just at a slightly different spot in the phase. This one is up, this one is already on the come up, and this one is maybe, you know, going down. Okay, just like they have here. Okay, there's just the timing is slightly different, forwards or backwards. Okay, and it's made that way by the power company. Okay, something is generating these sinusoidal waveforms that are slightly out of alignment in this way on purpose. Okay, in our three-phase power. Okay, this is the stuff that's coming off of the telephone pole. When you see the three lines coming into a building from the distributor, very often it's for our three-phase power, for our big stuff. Okay, and they are 120 degrees apart. Okay, that's on our unit circle here, right? If we separated it out, I didn't hit the center there very well. But if we chop that into thirds, our 360 degrees, okay, one will be here, one will be here, and one will be here. One way, I don't know if you guys have ever seen this, but one way to visualize a sinusoid is if we take a ball, oh, I got a terrible circle. If we take a ball on this line, we look at one spot on the ball and then we roll it. And where that point crosses will kind of look like this. Okay, the ball will roll down, and then it'll roll up, and then it'll roll down, right? That's our sinusoid. So if we have a ball that starts here, and a ball that starts here, and a ball that starts here, that's our 3 phases, okay? And if we follow the 3 starting dots as they trace out a path, okay, we'll see our out of phase sinusoid. Okay, that is, you know, the one that starts here, the one that starts here, and the one that starts here as it traces out the sinusoid. Okay. Now, between these 3 leads, right, these 3 wires that are coming into the house, we have different ways that we can wire them together in order to get our output voltage. You know, that's the additive one that rides on top. That is our output, right? The thing that is going into our load, essentially. Okay. So there's 2 ways that we can go about it. This is the Y connection. They spell it weird, W-Y-E, but it really, you can think of it as a Y, like the capital Y, but inverted. Okay, you could draw it the other way if you wish. But we have a common center. This is our ground, okay? This is like our reference point, right? And then we have our 3 phases, A, B, and C, in our reference point. Okay, here, we're actually using each of these others as a reference. So each of these points are referenced to each other. So A and B are connected, so they have a node here and here. A and C are connected, and B and C are connected as well. Okay, and I'm gonna show you why we do this. Okay, but essentially we are connecting in a star connection or a Y connection, everything's common to ground, or a series connection, also called a delta connection. Okay, that's how you can remember it. Delta, or A delta in the sciences or mathematics, is triangle. Okay, the mathematical delta symbol kind of looks like that. It's a triangle, looks like a triangle. Not too hard, okay? Now, the voltage that comes out, because one is parallel and one is not, okay, we get parallel or series voltages out of it. Okay, so the delta connection that we get down here between any 2 of these points is going to be different. It's going to be a higher voltage at 240 volts than any one of those connections, A, C, or B, to ground. Okay, it'll be 120 or 208 volts. All right, when we're talking about putting multiple generators in parallel, we have a huge load that we have to, you know, source. Maybe a hospital went down and we need to keep it powered or something. How do we do that and not cause things to explode? All right, they definitely have to be the same frequency. They definitely have to be synchronized. All right, because otherwise, what can happen is that one generator will feed in a positive voltage to the line, and then another generator, if it was perfectly synced in the opposite direction, would put voltage in the negative, and they would perfectly cancel each other out. I don't even know what would happen. I don't think they would supply useful amounts of power. I think it would just kind of heat up the wires. Okay, but if you had 2 generators that were perfectly synced, you know, you had one like that, and then you had another one like that, or they were, you know, synced pretty well, maybe they were a little bit out of alignment, they could still provide useful amounts of power, right, or current or whatever, okay? Now, one way that they do this is with lamps, essentially. They have a really clever formation. So I've only seen this done once, is actually someone was turning on a power plant. So they were onlining a power plant to hook it onto the network. So what they were trying to do was to get the power generated by the plant to mesh well with the power generated everywhere else. And they have to turn on the plant at the precise right moment in the curve so that it won't destructively interfere. It will add to the system. Okay, that also has a power factor effect. Okay, I'm gonna just take a minute and see if I can find that video. It's just a short. But give me 1 second. So power factor, dark light. I might find this later and then just send it out. Damn, I can't find it. All right, well, I'll maybe look back and see if I can find it, but essentially, there's 2 lamps that will slowly flash. The right one will flash, then the left one will flash, 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 and then they kind of sync up, where one will slowly flash until they're both lit for some amount of time. It's like 2 sounds that are syncing up, and then you'll kind of hear them wub together. That's just like what they do here. They see that these 2 lamps will come on in phase, and then they throw the switch, turn on the generator, and then the 2 generators are perfectly in phase, according to that indicator. And they won't destructively interfere, they will constructively interfere. All right, so the next part of the chapter is, is a reading exercise. Because it's mostly like maintenance stuff, troubleshooting stuff. You know, what to do if your brushes on your motor or generator get dirty, if your bearings go bad, you know, maintenance on your oscilloscope, okay? These things can be just read later on, okay, or already read in your book. But for now, we're gonna keep moving on, keep chugging through chapter 13, okay? Any questions for anything in the previous chapter? Okay to keep going?
This is all in the system?
It will be by the end of tonight, yeah. Yeah, I'll do it pretty much right when I get home. So I'll throw them up there. Okay, so this chapter is a mirror of our other chapter. The components are pretty much exactly the same. All right, we still have a magnet, permanent magnet and electromagnet. We still have a commutator with wipers, okay? It's just rather than having motion come from outside the system to create electricity, we are using electricity to create motion. The same physical principles are in effect. It's just a wire moving through a magnetic field or a magnetic field moving through a wire, but the outcome is, you know, inverted. Okay, but everything that we just talked about is still in play. All right, so the theory of operation at its most basic is that we really are just getting a magnet to kick over. Okay, that if we put a magnet in a magnetic field and that magnet will want to turn over to try to get to kind of like the position of least resistance, right? It'll move until the force on it moves it into a position of where it wants to be. But then if we were to switch the magnet, you know, if we were to switch the poles at that resting position, it would want to kick over again into a different position, into the other 90-degree position until it's dead again, right? But what we can do to not, you know, get it stuck, because what it'll want to do is it'll kind of get stuck in between our 2 magnets, and it won't be able to kick over because the path of least resistance will be here. So we want to get it to kick over again. The way that we do that is with a slip ring, okay, or a commutator. that we keep inducing a force on this to keep it turning it over, that we could swap the polarity on the magnets again and then continue the motion. Again, all in the name of getting the motor to kick over. Okay, is the commutator is a slip ring. Right? So that is for a permanent magnet motor, okay? Where this is permanent magnet, it's just like the magnet exists and it has a magnetic field. But what could happen too is that we could also induce or control this magnet too, okay? So we not only have our armature that we can control, this wire, but we can control this wire as well. So we have some additional complexity there. That way we can decide to energize the electromagnet here, or we can energize the electromagnet inside of the armature. Okay, get it to kick over. What we're actually talking about here is our laminated soft iron cores, right? Our sheets, our poles, and enamel covered copper wire. It's wire, whenever you guys see enamel covered or lacquer covered, it's like a really, really thin insulator, right? It's a wire that looks like it should, conduct anything you touch it with, but it's not actually conductive. There's a really thin layer of material that's separating one wire from all of the wires that are next to it. So when you see a motor and you see all those bundles of wires, they're not actually touching each other. It's kind of like a long wire that's just formed into a coil. Okay, enamel covered wire, a lacquer covered wire, all that good stuff. Enameled wire, right? Oh, All right, so this is what we were talking about, where we can have more than one pair of coils as well, right? So we were talking about more coils is more better inside of a magnetic field. So what we can do is we can have not just one coil in our field, but many coils that are slightly offset. So if we look at this from the top down, one coil goes this way, one coil goes this way. You can add even more coils. It just means that, when you're in a certain position in your rotation, you're not very weak. The motor can still kick over. You still have some coil within that field that's seeing a good amount of strength on it, okay? All right, so the counter electromotive force, if we are causing a motor to move within a field, an electric field, okay? At the end of the day, it's still a piece of metal moving in a field. So we're going to get a resulting voltage from that. Okay, just because we're causing the motion doesn't mean that the motion is not happening. So that motion is going to cause a counter force or a counter electromotive force, CEMF, okay? That counter force, okay, scales with, strengthens with speed, field strength, and our constant K. All right, K varies in different motors, different motor types, all that good stuff. All right, I just remembered I didn't take attendance. I'm gonna do that real fast before I forget. Oops. Quinn? I think I saw him earlier. Gail? Ooh. Luis? Thank you. Minold? Thank you. Joseph? Thank you. Jackson? No Jackson. Brett Hull? He contacted me. Anthony? Pascal? Thank you. Victor? Thank you. Alexandro? Alejandro? Levon? Nope. Jose? Thank you. Kevin? Nope. Christian? Nope. Emily? Thank you. Dulce. Thank you. Adam. Thank you very much. Okay. All right. Current slide. Okay. All right, when we're talking about the current flowing through the armature, all right, that is the current that is flowing through our coil. Okay, we have a coil in a field, right? So the current I traveling through this coil in our field is our armature current. I want you guys to understand that. That's going to come up later. Okay. Makes sense that the current flowing in here is essentially the resistance of this piece of wire, the voltage that is induced in this piece of wire by this EMF divided by its resistance. So that's the amount of current that flows as a result, right? Okay. As our armature moves less slowly, we have less EMF. As it moves more quickly, we have more EMF. Fun fact, I guess, well, all right, a fact is that by measuring C EMF, this is one way that we can measure motor speed. As a motor that moves faster, we can see a voltage rise and fall as it moves faster or moves more slowly. So as it moves at all, we will see a small amount of voltage kind of resist that or rise to that. So as the speed is constant over time, it'll kind of be that constant level of voltage. And if we were to ever raise it up a little bit, it would raise the voltage proportionally that we would see on that armature. Okay, so if we characterize that motor, we see some amount of voltage per some amount of RPM. We can get a really simple speed controller that way. Okay, we don't even have to have like much instrumentation or sensors or anything. It's just the actual motor itself and a voltmeter, essentially. Okay. A couple things that we need to know about stalled motors. Okay, weird things happen when a motor isn't moving. Okay, one thing that you need to know is when a motor is stuck, right? So if I have a motor that's turning and I have a rock or something that it hits and it can't move anymore, okay, and I'm continually energizing that motor, right, with my positive voltage or whatever, what happens is that a motor essentially just looks like a bare piece of wire that's shorted between your positive supply and ground. It's like it becomes a really low resistance resistor that you just dump all that energy to straight to ground. That's why motors heat up so much when they stall. It's also another reason why motors, when you first turn them on, use crazy amounts of current. Okay, there's something called a surge current that happens. So here our motor's not on yet. This is our current over time. Okay, something that happens is we'll get a huge inrush current, huge, ginormous, like 100 amps. And then it quickly settles back down to whatever its operating current is, that's all the way down here, and then carries on until you turn it back off. Okay, this inrush current happens when the motor isn't moving when you first turn it on. Okay, the inertia of it, the momentum of just sitting still, not moving anywhere, suddenly shunts a huge amount of energy to ground because you're just moving it into a wire. It's not until that motor starts moving a little bit before the energy that's going into that armature, the energy that we're putting into that motor, starts to get put into the motion and doesn't just get dumped to ground as heat. Okay. So this also happens if something were to suddenly stall a motor. If a motor, has been started up and has been running for a long period of time, and we suddenly stall it, something gets stuck in the works, you have huge current spikes like this, and you can melt a motor real easily. For example, if a fan gets stuck or something because it's just dumping current down to heat, the windings will melt themselves, actually, if it's allowed to run while stalled for long enough. So DC motors, very often are controlled some kind against overload. And there's all kinds of different methods of doing that. There's mechanical methods. For example, lots of times it will be a piece of metal, and that piece of metal will heat up and cause a disconnection to occur. The simplest being this bimetallic contact. Okay, it's again that piece of metal that I was talking about before that was so common in thermostats that changes its shape according to temperature, and when it goes over some temperature, it'll warp. And once it warps sufficiently that it removes two contacts from each other, it's like opening a switch, and it removes the flow of electricity. Okay, this is a motor that can save itself, essentially. When the temperature eventually goes back to normal, right, you figure out that it stopped and you remove the stuck condition, it'll continue to work and not have its windings melted, right? When we're talking about protection to put on a motor, right, that's usually something that, you know, the person is responsible for buying. You buy a motor, and then you have to figure out how big of a fuse to put on the thing, okay? These are a couple of rules of thumb for those devices. So the reason that they're rated differently is that they'll trip differently. You know, some fuses are slow blow. It takes a while running at that energy before it'll run. Others are kind of like testier than others, are more sensitive. They'll trip more easily, or they won't restore as easily. Okay, so these are some good rules of thumb for that. All right. I'm gonna go through this one, speed regulation. Okay, so just like DC generators, there's different kinds of motors. We're just talking about the mechanics are the same, but it's how do we wire those mechanics together, right? Armatures and field windings. Okay. Here is a chart that I want you to know. I want you to know about shunt motors. Remember, this is the parallel motor type. This could very well be on the test, be on the final. Okay. More than a few questions, even on the homework too. Lots of points on the homework are just asking you, telling you about a certain kind of generator or telling you about a certain kind of motor and asking you which one is it talking about. Okay, you're going to need to be able to know the characteristics of each. Okay, so here, again, we're talking about how are the field windings, the thing that creates the magnet, wired compared to our coil that moves within that magnetic field, okay? So in the series case, they're wired together, okay? The thing that's moving within our field is essentially the same wire, one continuous wire, with the magnet that's creating that field, okay? The same power supply runs through both. Okay, so sorry, here is our shunt motor or the parallel case. Okay, so whatever voltage we put on our armature also goes onto our shunt. It also means that whatever we're using to create the magnetic field within our motor, we're also using that same voltage to create the counterforce within our wire that gets it to kick over. Okay. All right. Okay, so this is one thing that I wanted to touch on. There's a whole chapter on transistors. One that you probably haven't heard of before is the thyristor. Okay, the thyristor, or its more modern incarnation, the triac. Okay, I'll talk about that in a second. It sounds like ancient science fiction, but it's actually modern day stuff. A thyristor, or a triac, as I'll explain in a second, is like a transistor, but for AC electronics. Okay, transistors are DC, voltage on, voltage off. They don't like to pass negative voltages. thyristors and triacs are devices that we can, by putting a voltage on the gate or not, by supplying a AC voltage here or not, we can allow current to be conducted through this device or not. It is a switch, a solid state switch. There's no moving parts involved. It's just silicon. But the appearance of voltage or not on a gate, okay, on one pin of that device will allow energy to pass through it, okay? So the downside for a thyristor, again, I'll leave it as an exercise for the reader, is that it can only pass on the upper half. Oh, dude, really? It was working so well. It can only pass the upper half of the sine wave. Okay, so thyristor, extremely convenient device, right? We don't have to worry about mechanical switching like with a relay. But it turns our raw AC signal like this, it just turns it into this. It doesn't pass the negative lobe. It's just missing. We're missing out on that energy. It's not burned off. It's just not being transmitted. It's not passing through the device. Okay, so if we have a fan, that motor will really only turn on, at half of the time that it should be turning on. Okay. A triac instead passes the full wave. Okay, where it kind of like as expected, it'll pass the positive and negative lobe, so it'll push and pull the electrons just as we expect it to. Okay, so the difference between an SCR or a thyristor, this is that symbol, and a triac being this symbol, again, it's more like a transistor for AC, is that it will pass both bumps of the signal. Okay. All right, different kinds of motors. Digital encoder. All right, so I just want to go through one more for motors and then we'll be done for today. So this is the breakdown of almost every motor that you'll ever see. All right, you guys have seen tons of these, comes in a can, heavy as hell, right? The outside part of that can is just sintered metal. It's pressed together in a mold, in a sand mold. It's mostly for cooling, actually. It's a giant heat sink, as well as mechanical rigidity. Almost always have a fan on the back with some brushes and bearings. Here's our commutator section. All right, this is the one that it essentially connects all of our different coils, right? We might have 30 or 60 coils in here, and then makes them accessible. So if we have wipers, right? If my fingers were graphite that could conduct electricity, right? And I touch them here, as it turns, I would be connecting to two different sets of coils. And as it turns over, I would be activating different sets as it cogs over. Here are our laminated sections. This is the thing that receives and boosts the magnetic energy. Okay, and then this is just a simple bearing, again, for mechanical rigidity. All that's shoved together in a can, and then you just apply AC or DC voltage to it accordingly, right? And then again, it's just, there's a few different types of motors. Okay, I keep trying to use this marker, damn it. Okay, there's permanent DC motors. That's where it has a magnet built into it. Okay, and then really we just charge the armature to get it to move. There's another one where the magnet inside is actually an electromagnet. Okay, so we can vary the strength by applying voltage on the electromagnet or the armature. Okay, so we're kind of doing double duty here, where we can get more power out of it. It's a more efficient device. Okay. Another type of motor is a stepper motor. We'll probably go into that next week. Just know about it for now. Okay. But all of these just have coils create a magnetic field, and then another coil that reacts to that field, that receives that motion or reacts to that motion that we can control or is controlled. Okay, and that's pretty much it for the main motor types. There's more mechanics besides. Could probably have a whole lecture on that, but I'm willing to call it there for this chapter.
Thank you.
Yeah, thank you. All right, so like I said, I'll get this up tonight. I'll get all the chapters actually, so if you guys want to read ahead a little bit through the rest of the term, you can do that too. Any questions, let me know. Feel free to send me an email. Otherwise, I'll see you guys day after tomorrow at the lab.